a second on that. All right. And so what I'm going to do is present to your screens. And so you might want to go down to the bottom right corner and click on the three buttons and choose full screen or something like that, kind of maximize what you have there. Okay, so let me see if I can project. All right, now I'm going to okay, so I'm assuming that you're seeing that PowerPoint. I'm going to just skip ahead. Oh boy, a lot of slides. Okay, 2.5, that was when we were working on, and 2.6. Pardon me. All right, so solutions to 2.5, number one. It's pretty easy, actually, I think. Let me see, somebody may be trying to get into the meeting, so let me just do this for a second. Move this to a different screen so I can see what's going on. Okay, yeah, somebody was trying to get in. All right, so I'm going to project back again. Okay, so back to 2.5, number one. I guess we want to make sure we get this hidden line right here and there for that crease that's going across right there. Other than that one's pretty straightforward. This one has the oblique planes. Pardon me. And so they're going to look kind of weird in this view over here, but we locate them by counting our grids. And since we're going in a half a grid right up here on the top, let me get a pointer out here. So right up there, we're just going in a half a grid. So we're just going to go in half a grid. I have trouble seeing that yellow. I'm going to change it to green. Right there, we're going in half a grid on each side. And then we see a full grid up here on each side. So we're going to come in that full grid right there. And we just keep doing that and locating points. And eventually by connecting all the points, we find out what those oblique planes look like. And so those oblique planes are up here as well in our top view. And there's one over here. And then we see that crease where the two planes meet. And so if you recall, the definition or pretty much of an inclined plane is that somewhere in one of the normal views, then a inclined plane is going to appear as an edge view. And an oblique plane will not appear as an edge view in any of the inclined planes. So we don't see it anywhere as an edge view. So I see we've got one person checking in on the chat saying testing. I'm assuming that you can hear okay now and everybody's okay. So you can either send chat or just unmute yourself and let me know. All right, so 2.5, number 3. What we want to watch for here is we have this arc coming around in the front view and dropping straight down right there, which means we're going to get a visible edge up here in the top view. And then the arc goes, or it comes from that sort of vertical plane into an arc that blends in right here. And remember, we call that a run out. And so the run out is happening here and here. And so when we have that run out, we don't have a visible line across. And then, of course, this hidden line here represents the back edge of that half round that we have. And then we have this half round over here coming across like that. And we will have a hidden line for that cylinder that we see here and here in our view. So we'll need a center mark. Center mark needs to come out past the edge of this arc as well as the hidden hole or the hidden cylinder. All right, so this guy, you've got two stadiums and you have a stadium cutout that goes all the way through, and then there's a notch on the back edge of that, and so we get some hidden lines for that notch, and we get hidden lines in the top view indicating the outside edges or the quadrant where that would project up there. And then over here on this side, same thing, we have those hidden lines where that goes through, and then we have the notches on either side. I think this guy looks a little tougher than it actually is. And if you drew it, if you thought that this thing that sticks out right here was on both sides, you know, it's kind of hard to tell. It would probably have shown if it actually were on both sides. So we need to have center marks. And you can see there's a gap right there where that center mark comes down and it doesn't blend into this visible line. There should be a gap right there. I think there is on the original, but when I do a screen capture, I may lose that. So right here, we actually have a visible line with a hidden line running behind it, so the visible line has precedence in that case. All right, this guy, where it gets weird is you have a hole right here intersecting an inclined plane. Of course, it's doing that on both sides. And so if you look where the hidden line intersects the plane and you project straight up from there, that would give you where this elliptical hidden line shape that you're going to have would, you know, the farthest point to the right on it, and you would project from where the hidden line intersects the plane and up, and that would tell you where it is on the left-hand side. And the ellipse will be the full diameter, which is 1. And then you mirror that over here on this side. And when I say mirror stuff, in AutoCAD there is a command called mirror. And so we actually do use that. And all we would draw in AutoCAD would be half of this part. And then we would mirror it, and we would use this line right here is what's called the mirror line. And that's sort of, you could imagine it like a hinge. And we would just mirror everything to the left of the mirror line over to the right of the mirror line. We do the same thing here. You could just draw half of this object and mirror it over here to this half. Okay, this guy, you've got to watch out for the hidden lines in the top view. And so hopefully you got those figured out. So this vertical plane on each side that runs through, and then this crease that you have right here goes on through up here. And over here it's not too difficult in the right side view. This one, a lot of people miss this one for some reason, and I'll point out the things that people miss. Right here, you have a short visible line coming across and a short visible line coming across right here. So you would want to have a gap right there for your center line, and you should have a little gap on this side. Then you need your center mark for both of those stadium shapes, and you repeat that over here on this side. You would want to extend this line out a 1/4 inch over here on each side, and then a quarter on this side over here. And then up here in the top view, you're going to have a visible line to there, which would be that edge right there on both sides. And then the quadrant of that stadium cutout becomes a hidden line in the top views. And over here where you have the center line, there should be a small gap right there where your center line begins. This one is the most difficult one on sheet 2.5. And where it gets difficult is in the top view, especially. And so you have this cutout right here that goes all the way through the part. So you can draw your hidden lines in from the side over here. And you see that that hidden line hits on this arc right here, and that is to the right of this point right here. All right. So we actually need to project up and find out where the edge of this visible shape is over here, where that cutout is. And we do the same thing over here on this side, project up to there. And so we have a rectangle that's a visible rectangle in the top view with hidden lines extending out from it. And people seem to have trouble with that one. It's understandable. And a lot of times folks don't take this, they just assume this visible line is in line with this visible line right here. You need your center marks on either side. And then over here you have a hidden line which represents the quadrant of this half round that's cut out. And then we still want to show those center axes or axes for both of those filleted corners. Remember, we call this a fillet. Now, the only reason we call that a fillet is because the AutoCAD command is the fillet command. What designers actually call that, because it's an external corner, that's called a round and not a fillet, but the command is the same. The fillet command, you do rounds and fillets. Fillets are inside corners. All right. So 2.6, number 1. This one's pretty simple. As long as you get those hidden lines right there, you understand that this goes. See, it's hard to tell that that doesn't go all the way through, but if it didn't go all the way through, you would need to see some kind of indication right there, because you don't. You have to assume that that goes all the way through. All right. So hidden lines over here for that. Okay, on this guy we have an oblique plane, and again we just need to find the points where the 3 points that define that plane, and then just connect the dots. And so that's really the only way we can create that plane right there. And so you can see it's not an edge view in any. I mean, the plane itself is not an edge view anywhere. We do see some edges of the plane. So the other planes, of course, are inclined. And remember, we said inclined, you'll see an edge view. So right here, we're seeing an edge view of this inclined plane. And we see an edge view over here of this inclined plane that's up here. So these are inclined, of course. So how would you get a full size, like a true size and true shape view of this plane right here? Well, somehow you would have to rotate this part around until your line of sight was normal to this plane right here. And that would take a couple of revolutions of this part to get there. The great thing about CAD is that we can create a 3D model of this, and we can easily look at that plane normal to the plane when we have a 3D model of it. But in the days of 2D drafting, this would have been called a revolution and a development. It would have taken a little while to rotate this part around until finally you get to the point where you're actually perpendicular to the inclined plane. All right, this guy is a tough one. So we have a cylinder intersecting another cylinder. And because they're not the same diameter, the intersection results in a saddle. And so we can see in this section view how this dips in and how this guy dips in over here, and also where it intersects, where the hole intersects the other hole, we're also going to get a saddle shape. And we're going to see those in the top view. And so the way we determine where the saddle is we look at where this hidden line comes across here and where it intersects with our circle. And we're going to project straight up to right there. And that gives us the depth. Sorry. Let's see what's going on here. We need to go back here. There it is. That gives us the depth of that. And this one gives us the depth of that guy there. All right. So one of the things we really just have to be aware of, I think, when we're drawing multi-views of two cylinders intersecting are, we have to ask ourselves, are they the same size? If they're not the same size, the intersection is going to look like a saddle. If they are the same size, the intersection will look like a V. All right, so just keep that in mind. And I think we've got that'll come up again. All right, 2.6 number 4, it's not very difficult, but I want to point out right here that this fillet in the top view and the center of this stadium shape, they are not concentric. So we need to show two different center marks on this guy, because the radius of this fillet right here is only a half a grid, right? And the radius of this guy here, though it's a half a grid, it's not located at the same point. And we can also, these are pretty significant radii over here. They're 1.5 radius. So we definitely want to show a center mark for those. Probably on a drawing, what we would wind up doing is having a leader like that with an arrowhead. And this would say R1.5. All right, so this one, we have a cylinder right here that has a diameter of 2, and it's intersected by another cylinder with a diameter of 2. And so what we said was that when you have two cylinders of the same diameter, you're going to wind up with a V shape on the inside. So that's why I created this 3D model of this part cut in half, so you could see that. And where that shows up is going to be over here on the right side view. So we're going to, first off, we're going to have a saddle right here because we have a hole, this hole here, intersecting a larger cylinder. So we will get a saddle here, and we'll get a saddle on this side. But then we have this hole intersecting with a hole that goes through from the top, this hole up here. And so because they go all the way through, you're going to have a hidden line that comes all the way across. So I said a minute ago you get a V shape. So here's the V shape, and then here's the V shape on the opposite side. If they didn't go all the way through, there would just be a V shape here, but you need both V shapes. So when you sketch this, if you didn't get that correct and then you went and looked at the solutions, you may have wondered why it looks the way it does. But it's just that rule of holes intersect or cylinders intersect, same diameter, you get that V shape. All right, on this one, we have some concentric arcs. So we need this center mark here that extends out past the edge. But down here, it's only the center of this guy, so we just need to come out about 1/4 inch past the edge of this over here. And things like that are going to be important when we're drawing with CAD. You know, I'll be looking for how you handle the center marks and things when we're doing this in CAD. And we have lots of hidden lines in the top view and some in the right, but other than that, this is not very difficult. All right, this guy has a couple of tricky things. You have a plane right here. Of course, you're normal to that plane, so this is true size and true shape in the top view. That's this coming across here. You have an inclined plane. And then you're going to have hidden lines for this vertical surface here and this vertical surface here, and those project up to there. And then you have a hidden line for the quadrant of these holes. And then you've got this edge right here, that crease in the back, and that's going to project up to here. And then all of those things that could project across from the features of the front view. We've got this guy. Now, this guy right here, you can see because this is cut out, that this guy should really not make it to that grid. It should just be up just a little bit. And I think because of the line thickness, we sort of lost that on this. But that bottom edge should be not quite to the grid. This one is difficult. Okay, so in the front view, it's not. It's pretty easy in the front view. And the side view shouldn't be difficult until you sort of have to look at, what are these hidden lines doing? So you've got a hidden line right here, and you've got another surface right there, so that's going to give you these edges. Then you have a vertical edge and a vertical edge, and there's one on the back side, and so that's this hidden line and this hidden line that becomes visible when it gets up to there. The same way over here, we have this vertical edge, which is hidden because it's below this line there, and then it becomes visible up here, and then we have the hole going all the way through. Now up here in the top view though, you have a vertical edge, which is this hidden line here, and then that blends in to this middle piece right in there, so we lose the vertical edge. This is the hole excuse me, on either side. Then we have an edge coming here and an edge coming here, so all that's hidden. That represents what's going on in here. So that's why I created these 3D models, so to kind of help you visualize what it looks like from both ends of the part. But this is definitely one that students struggle with. So. And this is the last one, and again, it's a tricky one. So you sketch your front view and then start projecting. So let's look over here to the right side view. This vertical plane that we have right in here gets cut. I mean, we're cutting out right here. So if we project across right to there, you see this line does not make it all the way up to the grid, although it does make it over here. So this part right in there, that makes it all the way up to the grid line, and it does the same down here. So for 2 grids it makes it, but for 1 grid, and same on this side, it doesn't quite make it up there. Now look over here in the right side view and look at this line right here. So why doesn't that line make it all the way to the top? Well, here's why. It's this plane right here in the edge view, and that plane goes up, but it doesn't make it all the way to the top. It goes tangent to this cylinder before it makes it to the top. And same way down here, we project that, it goes tangent to the cylinder. And at that point, this is a run out in here. So what we do is we go to the tangency point and we project across, and we go to the tangency point, which is about right here, and we project across. And that gives us some idea of how long we should draw this line. So if your line went all the way to the top and all the way to the bottom, it's going too far. And you're going to have something similar to this come up. I don't know if it will be this week, but it'll probably be next week on one of the things you're drawing. You're going to have a run out like this where it goes tangent, and you're going to have to deal with that in one of the views. So here's what's happening in the top view. You have this edge here and this edge here, that plane. It's running uphill, and it's running uphill on this side. And it doesn't make it all the way to the top. You can see it comes up and then it hits the tangency. So we look and we find that tangency point and we project up. And that's how far we know this line comes up, and then it becomes a run out in there, so there's no hard edge. And same way here, we find this tangency and we project up. Now, those might line up with the edges of this hole, but they're separate features. All right, so if what I did here went a little fast, I'll post this video after class in the recorded class meetings, but then also you can go back and check the solutions if you have any questions about this stuff, or you can ask me. All right, so that ends chapter 2, which is the multi-view sketching, and you're probably glad for that. So now what you're going to be doing is applying all of that to CAD drawings. And in a normal semester, I think I mentioned, we would actually do a little board drafting. Let me see if I can get out of this guy. And I'm going to show you a different PowerPoint here. All right, so this PowerPoint is from chapter 3. And that's the traditional drafting chapter. And so one of the things, though, I wanted to touch on in the traditional drafting chapter are drawing sheet sizes. So let me get a highlighter again, get a color. All right. So there's standard sheet sizes, and we may have already talked about this one, where 8.5 by 11 is called an A size sheet. And some offices use a 12 by 9. And even though the sheet here is shown vertically with the long edge running north and south, when we use those in a technical drawing, the long edge would run east and west, and the short edge would run north or south. But anyhow, this is what we call an A-size sheet. So if you can remember that 8.5 by 11 or 12 by 9 is an A-size sheet. And then if you can just remember that if you put two of those A-size sheets, turn them vertically, put them side by side, what you get is a B-size sheet. Now, if we were on campus, the printers we have in our classrooms can print A and B. So the capstone projects and big projects, we print 17 by 11. But most of the projects get printed 8.5 by 11. If you take two B-size sheets and you put them side by side, you can see over here, you get a C-size sheet. And if you took two of those C-size sheets and you put them side by side, you would have a D. This total thing here would be a D, and if you put two D's side by side, you would have an E. And so sheet sizes can get kind of ridiculously large, but it's kind of normal. Like I've seen some of the sets of plans for some of the high-rise buildings downtown, and they're just hundreds of sheets, and they were all E size, so it was a big set of plans. And that didn't include everything. That was just some of the structural stuff. So in your book, it talks about, A size, B sizes, and talks about combining these sheets together. And one of the things it points out, I apologize that I've drawn in that area, is that there is a standard ASME Y 14.5-2005. That's called the Decimal Inch Drawing Sheet Size and Format Standard. Now, in architecture, The sheet sizes, they go with the larger size sheet. So you can see they start with 12 by 9, and then they double that to 18 by 12 and double that to 24 by 18. And so their D size is 36 by 24. Where in a mechanical drawing, this would be 34 by 22. But the truth is that organizations and industry, they kind of blend these. They don't stick exactly to, mechanical isn't always 34 by 22. Sometimes it's 36 by 24. It just depends on the company and what their standard is. So we used to draw on this strong, thin paper called vellum, and that was when we were doing traditional drafting. And that was, vellum was this kind of thin paper that allowed light to pass through it fairly easily when you shined a bright light on it. And that was how you made blueprints, what we called blueprints, which were actually called blue line prints. And so there used to be a place, or there still is this place in town. It's called Miller, and it used to be called Miller Blueprint. And so everybody would have their blueprints made there, but now pretty much people copy stuff using more of a Xerox type process. And so a lot of these companies that were called like Miller Blueprint now call themselves like Miller Reprographics, because they've gotten into more digital graphics reproduction than anything else. And so what you would do is you would send a digital file, let's say in AutoCAD, to Miller and tell them you needed 20 sets of that plan printed. And they would open the CAD file with their CAD software, and then they would print it. And then you would come by and pick up those plans, or they would deliver them to the job site. So there's a place called Burke's. It's another old Austin establishment. And Burke's is also a place that reproduces blueprints and prints for job sites. And then you have your metric sizes, which are in millimeters. So those look a little weird to most people who grew up in North America. But we will do some metric drawings. And so when we do a metric drawing, it's important that when we set up our sheet size, that we set it up where the lower left-hand corner will have a coordinate of 0, 0. And the upper right corner up here, we might set up to where it's, let's say, 420, 297. And of course, that's in millimeters. And that would mean we count over in this direction 420 millimeters. And we count up in this direction right here 297 millimeters. And there's even a metric drawing standard. And one thing about ASME, American Society of Mechanical Engineers, if it's metric, they'll include an M in the standard. And so if we went back and we looked at that one that was not for metric, it would be exactly the same number, but no M is included in it. All right. So we talked a little bit about in this chapter about making traditional drawings, so we're not going to be able to do that. And so the good thing for you guys is we actually gain about a week, and that's 2 classes by not doing any traditional drafting. And but one of the things we get into in chapter 3 is scaling and what full scale means. And so full scale means that the size of the object in the drawing will be the same size after the object is manufactured. All right. So what we do in AutoCAD is we always draw everything full size. And so we, if we're drawing a house plan, we're actually drawing it 50 feet by 100 feet. But when we print it, that's where we scale it down. So when we send it to the printer, we may scale it to 1/4 inch equals 1 foot. And so, so that's just something to think about that's a little weird because you couldn't do that. Of course, if you were drawing on a drafting table, you had to scale it when you drew it. But in CAD, we don't scale it. We just, when we draw it, we scale it when we print it. But you should know what that full size means, that the size of the object in the drawing is the same size of the object after it's manufactured. And when you note that on a drawing, you note what the scale is. You could write 1 equals 1. And in that case, you'd be saying 1 unit on this drawing is equal to 1 unit after this thing is manufactured. You can write that as 1/1 or 1:1. And you can always think of it that 1 to 1 is like a fraction. If you wrote it like that and you divide the numerator by the denominator, you'll get 1 times. It will go in there 1 time. So we could say that the drawing is 1x if you wanted to, 1 times. So half scale means that the drawing is half the size of the object after it's manufactured. And so we would write that, if we were writing our scale, we would write it like this. So like I said, we draw everything full scale, but when we print it, that's where we might print it at half scale. So in the title block of the drawing, we'll always write what the scale is. And sometimes the scale is 1 to 1, and sometimes the scale is 1 to 2. And so if you divided 1 by 2, you would get 0.5. So you could say that the drawing is 0.5 times or 0.5x. Double scale, sometimes you have a part that's very small. And so in order for the views to show up, we draw it twice the size of the object after it is manufactured. So after the part's manufactured, it's very small. But the drawing's actually larger so that the machinist and the people making it are able to read the drawing. And so when we put the scale on that, we will write that our scale is 2 equals 1 instead of 1 equals 2. So this means that 2 units on the drawing equals 1 unit when the part is manufactured. And I remember being in my first drawing class, and I was all turned around about scaling. So when 1 unit on the drawing equals 2 units after it's manufactured, it means you've drawn it at half scale. When 2 units on the drawing equals 1 unit when it's manufactured, you've drawn it at 2x or 2 times scale. And so we have a bunch of different scales that we use. An engineer's scale, which we can measure decimal inches on. And we have a metric scale that we can measure millimeters on. And then we have architect scales that allow us to measure like a 1/4 inch and an 1/8 of an inch, and so on like that. And so there's a combination scale that you can purchase. The combo scale, the combination scale, looks like this. It's a 3-sided scale. And but what it has on it, it has a couple of the most common engineering scales, like it'll have the 10 and the 20. It will have some of the common metric. And so this one that says 1:100, that's your millimeter scale. And then it'll also have 1/4 inch equals 1 foot and 1/8 inch equals 1 foot. So it's a good combination of scales. If you're looking to purchase a scale, you might consider just buying a combo rather than all 3 of these scales. Obviously, if you work in an architectural office, there's going to be a bunch of architect scales around. If you did everything the metric system, there would be some of these scales around. But if you're a mechanical engineer or a civil engineer, you're going to see the engineer scale a lot in the office. So I'm just going to give you a brief look at the engineer's 10 scale. So you look on your scale and you find this 10 right here. This is tenths of an inch. Each mark represents a tenth of an inch. So when we get to right here, we're at 1.5 inches. All right. And so I'm going to keep going here a little bit. I'm going to break this number down for you. So when we read this number 3.125, the 3, which is to the left of the decimal point, represents whole inches. The first placeholder we have here represents tenths of an inch. If we have a second number, that represents hundredths of an inch. And if we have a third number, that represents thousandths of an inch. So when we look at this number right here, 3.125, the way a machinist would read this, they would call that number 3 and 125 thousandths. Does that make sense? Because they start with the smallest increment that you have, and then they put this entire number together. All right. So if you had 3.1, that would be 3 1/10. Okay. If you had 3.10, they would say 3 10/100ths of an inch. And if you had 0.100, machinists would say 3 100,000ths of an inch. It just depends on how far you're taking your precision. And that's what we call this, is precision, how far we take things. So if the designer gives you a sketch and has a dimension that says 5 or 0.50, and you come in here and change the precision and you write on the drawing 5.00 or 0.5, you change the precision from what the designer wanted, and that could change the tolerance that's applied to this. And so tolerance is this like allowable error we have when we manufacture something. It's very difficult to make something perfectly to size, and so we usually give a little bit of an allowance that allows us to veer a little bit off of perfect. And so this is why if the designer says 0.50, we don't want to say 0.500, because that would imply that the tolerance is much tighter. And if we just say 0.5, that would imply that the tolerance is looser. So just be careful of that. Now I'm going to skip through this part because we're going to come back and talk about thousandths and all that kind of stuff later when we start talking about dimensioning. But I do want to show you that a civil engineer can pick up that same scale and say that each of these marks right here, instead of being 1/10 of an inch, they could say each of those marks is 10 feet. And so to a civil engineer, that same 1.5 that we saw a second ago could read as 150 feet. And this point right here could read as 312 feet, 275 feet. So, to engineers, they can interpret this scale differently. A mechanical engineer might see those as tenths of an inch. A civil engineer could say, well, that's each mark is 10 feet. If they wanted, they could say each mark is 100 feet, each mark is 1,000 feet, and that would determine the scale of the drawing they were making. So this is the metric scale where each mark equals 1 millimeter. So when we get to right here, if you count each of those marks, you would see we have 30, so this would be 30 millimeters. You can see we're at 40 and 2 more, so that makes this 42 right here. And then we're at 70, go to the 7 and 4 more, so this would be 74 millimeters. And so we will be creating, like I said, we'll have a drawing or two where we'll use millimeters. And then when we start doing our architectural work, we'll actually use the architect scale. And so this is an example of the architect's 1/4 scale. This is pretty common, especially when you're drawing house plans and things like that. So you look at the 1/4 scale right here, and the reason it's looking upside down is if you lay the scale on its side, that's probably where it would be on this scale. And so each 1/4 inch, so from the 0 to where this hits right here, that would be 1 foot. And so if you went from the 0 to the 2, that would be 2 feet. From 0 to the 4, that would be 4 feet. But then these numbers that you're seeing here to the left, those are inches. So if you needed to mark 1 foot 4 inches on a drawing, you would take the 1 foot, and then you would go 4 of these marks right here to get your 1 foot 4. All right, so one of the things we do in this class, we'll draw a wall for a house, and we'll draw the sides of the walls 4 inches apart, for example. And so we don't have to use the scale to come in and measure that 4 inches if we're drawing these, because we can do that very accurately in AutoCAD. But if we were doing this on a drafting table, you'd actually have to use this area right in here and measure over 4 inches and put 2 marks, and then draw construction lines through there and eventually darken those. All right, so I think what I'm going to do is skip through most of this stuff here. But this is all in Chapter 3 about reading the protractor, circle templates, how to construct a multi-view drawing where you figure out where your front view, your top view, and your right side are going to be. The great thing about CAD is if we draw our front view someplace we don't like it, we can always move it, and then we can align the top view and side views to it very easily using a command called the move command. When you're drawing on paper, you've got to construct it where you actually want it to be. And so what we would try to do if we were drawing this on paper is, you see that distance right there, we would try to have that distance and this distance equal. So that required doing the math where we would take the total width of this sheet. If that were a B-size sheet, that might be 17 inches. And then we would take the width of the front view and we would take the width of the side view and we would add those two together. So we would add this, and then we would subtract that from 17. And whatever number we had after we subtracted the width from 17, we would divide that by 3. And that would give us this and this and this. In the same way, we would do that vertically. We would have our distances between views. We would take the overall height, subtract this depth and this height, and divide that by 3 to get these. So you guys don't need to worry too much about that. But what you will have to worry about is in a CAD drawing, you'll move your views so they're kind of balanced on the sheet. So we'll get into that more later. So you can see this drawing once you get everything added. And then I asked you guys to watch that video on developing a technical lettering style. So this is what I'm talking about. This is some really nice lettering in here. And so write like a designer. I gave you some tips and tricks on that. And in that chapter, you can print out some practice sheets. So here's some good technical lettering examples. And so my lettering style is somewhere between like this and this. It's a little bit looser than this one on the top, but maybe not quite as loose as this one down here on the bottom. So these are some sample sheets that you could practice your lettering with. All right. Questions? Anybody want to unmute and ask a question? Okay. So what I'm going to do next is talk about CAD. And so I'm going to pull up AutoCAD. It's down right here. It's this A down here on the bottom of my screen. So let's see, I may need to move this. Okay. So I think what I need to do is expand my recording window. It does look like I can do that without stopping it. So I'm just going to keep on going here. All right, so when you open AutoCAD up, this is what it's going to look like. In fact, I think I'm going to turn this video off.